Welcome to Unit 3, Trigonometric Functions. In this video, we're going to talk about circular trigonometry and the unit circle. So what I really want to do in this video is try to connect everything that we learned together and even add a little something in new that hopefully really solidifies what you know about trigonometry. So let's start with what we know so far. So we first know that we have a right triangle, and the basic trigonometry is if we're going to talk about this angle theta, and we know the trig functions are all based on the sides of this triangle. So we have the opposite side over here, the adjacent side, and of course the hypotenuse. And then again, we defined all of the trig functions. Like we know sine of theta is the opposite side divided by the hypotenuse and so forth, right? And even if we were to make the triangle bigger, the opposite side would get bigger, the hypotenuse would get bigger, but the ratio would stay the same, because even when I make a bigger triangle, or if I were to make a smaller triangle, the angle theta is not changing. But again, the opposite sides, the hypotenuse sides, and the adjacent are changing, but they're all changing within the same ratio. So that ratio of what sine is staying the same. Then what we did was we moved our thought process of angles to a standard position where we said, okay, instead of putting the angle in a triangle, let's put that angle in the coordinate plane, the XY coordinate plane. And what we really want to focus on is really the hypotenuse is the important part, right? So we started with the hypotenuse straight down here. And then when we rotate that hypotenuse and we stop, we create an angle. And that angle right there is theta. And that angle is really important because that angle is linked to the terminal side where it stops. So we said, okay, well, let's stop right here. And when we stop right there, we create a point x, y. And from there, we could make our triangle. We could draw that triangle straight down here and straight over here and make this right triangle. Sorry, it doesn't look very good, but you get my point. And then we say, okay, well, that's the triangle just like we had over here on the left. And the height of that triangle, the side opposite of the theta is the y coordinate, how far you go up. And the adjacent side or the base of this triangle is the x coordinate. And of course, the hypotenuse was the radius, because if we continue to sweep this around, we create a circle. So that hypotenuse is the radius. And we said, okay, well, same thing here. Now that we are looking at this through a slightly different perspective, sine is the y coordinate, which is, of course, the opposite of that angle, divided by the radius, which is like the hypotenuse of that triangle. So we were able to still maintain the same idea of what sine is, opposite of hypotenuse, but we do so through a different perspective of looking at it on an XY grid. And here's an even little bit more maybe solid example to try to really get you guys to understand this. So here we have three circles, right? They all have a center at 0, 0. And let's say the red circle has a radius of 3, the green circle has a radius of 7, and let's say the blue circle has a radius of 11. So let's draw an angle here, right? And I could draw an angle like this. And let's say that angle is a beautiful, wonderful 23 degrees. Okay, now notice that based on my three different triangles, I have three different points. The one on the radius of 3, the one on the radius of 7, and the one on the radius of 11. So clearly I have different lengths of radius, or in terms of the triangle, different hypotheses. And I could also draw a small triangle there that has a hypotenuse of radius 3. I could draw a medium triangle here that has a hypotenuse of radius 7. And I could draw a bigger triangle here that has a hypotenuse or radius of 11. Now, if I go to my calculator and I say, okay, what the heck is sine of 23, right? I can grab my calculator and figure that out. Anybody can just grab a calculator real quickly. Make sure you're in degree mode, of course. And sine of 23 degrees is 0.391. Now, of course, that's an approximation, but 0.391. Now, what does that 0.391 represent? It represents the, in terms of a triangle, the opposite over the hypotenuse. Or in terms of x's, y's, and r's, it represents the y divided by the radius. So the thing is that the sine value of 23 degrees is 0.391, regardless of you're talking about the red circle, the green circle, the blue circle. So let's look at the red circle, right? We know that sine of 23 degrees equals y over r. But we also know that sine of 23 degrees is 0.391. And we also know that the radius of that red circle is 3. So I can actually multiply the 0.391 by 3, and I can get my y coordinate. My y coordinate in that red circle would be 1.172. And again, that's an approximation. But that would be the y coordinate right here of that point. And now if I move and talk about the green, so I'm going to use the green color. If I talk about the green, I could still set up the, hey, sine of 23 degrees is still the y coordinate divided by the radius. But again, use your calculator. Sine of 23 degrees is 0.391. And I don't know what the y coordinate is. The radius is, again, the green circle is a radius of 7. So I could take the sine of 23, which again was the 0.391. I could times it by 7. And this time I get a y value of 2.735. So, of course, if you follow the y coordinate of that point, it's higher. Well, no crap. It's higher. It's a bigger circle. So what I'm trying to emphasize here is that, yes, the 23 degrees has not changed. But on each circle, the radius has changed, hence the y coordinate has changed, but the ratio of the y coordinate divided by the radius is still the same. So even if I take my y coordinate 1.172 and divide it by 3, I still get the same ratio, 0.391. Or if I take my y coordinate on the green circle, 2.735, and divide it by the radius of 7, I still get that same ratio, 0.391. So we have this understanding of trigonometry in triangles, but we also now have it in, I guess, circles that are created in standard position. So let's look at trigonometry, sine, cosine, tangent, one more way. And that is what we call the unit circle, right? I truly hope by now you have a good understanding that trig functions are ratios. So in triangles, we could see those ratios. And even if I make the lengths of the triangle bigger, that ratio stays the same as long as the angle is the same. And I could also discover this, like I just did, with angles in standard position. And even though I take that xy coordinate and I make it bigger with a radius of 11 or smaller with a radius of 3, hey, the ratios of the x, y, and the r's don't change as long as the angle stays the same. So one more way we're going to do with this is we're going to try to stay consistent. So instead of, changing the angle or changing the radius, we're actually going to leave the radius the same. We're going to leave the radius as 1. And anytime you have a circle that has a radius of 1, we call that a unit circle. Its radius is 1, whether it be 1 foot, 1 millimeter, 1 centimeter, 1 mile, 1 kilometer, who cares? It's 1. So let's look at that circle. So here it is. And if you were looking at that circle, you'd be like, well, how do I know it has a radius of 1? Well, I'm telling you it has a radius of 1, which means that this point right here would be 1, 0, right? The radius would be 1. And this point up here would be 0, 1. And this point over here would be -1, 0. And this point down here would be 0, -1, right? That proves that this has a radius of 1. And anytime I draw a radius, boom, draw a radius right there, you're guaranteed to know that that radius is 1. So again, I'm still on an xy axis. So this point on the circle is still going to be an x, y. And when I make my triangle, as we've been doing here, to represent this angle, now again, the height is still y, and the base or the adjacent side is still x. But now this is awesome, right? Because when I do sine of theta, and I say, listen, I just got done explaining sine is the y coordinate divided by the radius. But this is even cooler, right? Because what I'm doing is I'm guaranteeing that that radius is 1. And when the radius is 1, I'm not going to cancel it out. But if the radius is 1, 1 divided by 1, or excuse me, any y value divided by 1 is, well, just y. So now I get an even simpler way of defining sine of theta. It's just y. As long as you are on the unit circle with a radius of 1, it's just y, right? So again, let's talk about 23 degrees. Let's go ahead and talk about that 23 degrees one more time. Sine of 23 degrees, we know, again, is approximately 0.391. So if I say, okay, well, I also know that sine is y over r. But again, if that radius is 1, then I could just replace that with a 1. So what does that mean y is? 0.391. So that means that this y coordinate is actually 0.391. And how would I find the x coordinate? Well, that's cosine, right? So cosine of 23 degrees, we traditionally know as x over r. But if that radius is 1, well, then it's just x. Now, of course, I have to emphasize this is only going to happen when you're on the unit circle, but that's what we're talking about right now. So cosine is 0.921. So that would be my x value, 0.921. Because again, with the radius of 1, sine, you take the y divided by the radius. Okay, 0.391 divided by 1 is 0.391. And cosine is the x coordinate, 0.921 divided by, well, the radius 1. So I get 0.921. So there is my point that corresponds to 23 degrees. And let's actually, I really want this to be clear. So let's kind of zoom in on that first quadrant. I really want you guys to fully make sense of this. So again, I'm just going to, instead of talking about 23 degrees, I'm just going to talk about any just random angle we'll call theta. But again, the key thing is, since I'm on the unit circle, I automatically know the hypotenuse is 1. So when I have this coordinate here, x comma y, and I drop that down, that's my y value, and I come over here for my base that creates the right angle right here, that's my x value. But again, this is just, I'm trying to make this even more simplistic, right? We're trying to even be more consistent. When we talk about sine of that angle, you could look at it as a triangle, opposite over hypotenuse, y over 1. Or you could look at that as we're trying to teach you here, y over r, but the radius is 1. So it really makes it easy. So essentially sine of theta is just y. And cosine of theta is the same thing. It's x over the radius, which is 1. So that's just x. Now tangent does not involve the radius. So tangent is still y over x, of course. So we get these much more simplistic values. We get this much more simplistic understanding of sine, cosine, and tangent when we have a radius of 1. Again, all we're doing, we're still maintaining that same relationship between the side lengths. We're not changing that, but when the radius is 1, it just seems to make it so much easier. So let's do one more example here. Let's look at a value that we really love, 60 degrees, right? 60 degrees, somewhere right around here. This is a value that we just love. Now again, we're on the unit circle, so I know that this radius is 1, but I now know that this is 60 degrees. And as always, right, we're trying to find that x, and we're trying to find that y value. So if I drop this straight down, I make this right angle here, come over here for my base. Okay, this is awesome, right? Once again, y is opposite, x is adjacent. All right, this is all sinking in. But wait a minute. This is a triangle. We love these triangles. We absolutely, well, okay, I got to erase that. That's ugly. We absolutely adore the 30, 60, 90 triangle. It's one of our favorite triangles, 30, 60. Let's review quickly the relationship here. So the smaller leg across from 30 can be anything at once. The hypotenuse is 2 times that anything. And the longer leg across from the 60 is that anything times radical 3. So the problem is, if we try to move that triangle around, rotate it, flip it, and make it look like it does over here, the only thing I got to be aware of is that my hypotenuse is 1. So the hypotenuse is supposed to be 2 times the shorter leg. But again, I know the hypotenuse and the radius is 1. So if the hypotenuse and radius is 1, let's backtrack, right? So if that hypotenuse that's supposed to be 2a equals 1, that means a equals 1/2. Okay, so that means my a value is 1/2. Now that makes complete sense. If the short leg is 1/2 and the hypotenuse is double that, well, then it would be 1. And then the longer leg would be 1/2 times radical 3, or more simply put, radical 3 over 2. So how does this help me? Well, now I have created a 30, 60, 90 triangle with a hypotenuse of 1. And if the hypotenuse is 1, then I know the short leg is 1/2, and I know the longer leg is radical 3 over 2. So I come back over here to my picture, and I say, okay, let's talk about 60 degrees. Well, the shorter leg is 1/2 when the hypotenuse is 1. And the longer leg across from the 60 is radical 3 over 2. Okay, this is awesome. So that means that the x value of this point right here is 1/2. That's the x value down at the base there. And the y value is radical 3 over 2. But listen, we should have known that, right? We already know. Like, go back. Hopefully you guys are listening and you've been making your cheat sheets. We know what sine of 60 degrees is. Sine of 60 degrees, again, you could use this 60 degrees and say, well, that's a radical 3 over 2a, but the a's cancel, radical 3 over 2. But we could also understand it through the perspective of my y over r. So the y is radical 3 over 2 divided by the radius of 1. Well, heck, that's just radical 3 over 2. So what I'm trying to get across here is all I'm doing on the unit circle is making the radius 1. And when I make the radius 1, things just seem to work out nicer. And again, if you truly want to check me on this, use your calculator. You know, what is sine of 60 degrees? Sine of 60 degrees is 0.866. But again, if you don't believe me, I really encourage you to check. Radical 3 over 2 is approximately 0.866. And we love 60 degrees so much that we would definitely expect you to have the exact answer. So again, what I'm trying to emphasize here is that whether we have angles that we love, like 60 degrees, or angles that we don't love, like 23 degrees, it doesn't matter. When we're on the unit circle, we're forcing that radius to be 1. So everything still holds true when we talk about opposite over hypotenuse and adjacent over hypotenuse and y over r. But when the radius is 1, it just makes it so much easier. So here's a kind of a cleaner look at everything I just said here. So if t, I don't know why we're using t, whatever, it doesn't matter. Remember, it's an angle, right? So I usually like to call it theta, but I can call it anything I want. Here I'm calling it t. So let t be a real number and let xy be a point on the unit circle. So again, draw a picture. Here's a point right here. It's on the unit circle, x comma y. And let t be the angle that takes me to that terminal side. And what we're now saying is that we know for sure the radius is 1. So again, sine of that angle, I'm just going to call that angle t, sine of that angle is, again, y over 1. Well, that's just y. Cosine is x over 1. Well, that's just x. And tangent is y over x. And again, if you really need to draw the triangle to see that the opposite side is your y, the adjacent side is your x. Now, I do have to emphasize one more time here, and I mentioned this in the last video, that now we are moving to different quadrants. So you got to be super careful of where are you negative, where are you positive. Because if I'm in quadrant 2, like I am in this picture, the x would be a negative value. So when I find my cosine, it would be negative, right? And just to confirm this, right, you know, find an angle that's in quadrant 2, like 150 degrees. 150 degrees is definitely in quadrant 2. And cosine of 150 degrees, which is the x value, is negative. Don't believe me, go to a calculator. Cosine of 150 degrees, telling you it's going to get a negative value. And that's because when you're in quadrant 2, the x's are negative. So, now we have 3 ways, all the same, just different perspective of understanding trigonometry. We can look at an angle theta in a triangle, and we know the relationships that are based on that opposite side, the adjacent side, and the hypotenuse. We could also build that angle within a circle on the standard position here. And we know that when you're on an XY grid, you stop at x comma y. But again, like we saw that earlier example, you could have a radius of 3, a radius of 7, or a radius of 11. But again, it doesn't change the fact that across from your angle is the y, adjacent to your angle is the x, and of course the radius is the radius. Now, you do need to remember, of course, the big connection is that x squared plus y squared equals r squared. And that connection is true in the triangle as well, right? The adjacent squared plus the opposite squared equals the hypotenuse squared. That's Pythagorean's theorem. But then what we're doing now is, again, we're actually doing the exact same thing. We're just saying, hey, listen, let's make this even more simplistic. Let's have the radius always be 1. So therefore, when we create this triangle where the opposite of the angle is y, the adjacent is x, but with a radius of 1, boy, we can really dumb this down and just say, hey, sine of theta is just y. It's just y. It's that simple. So it really makes this hopefully really, really easy to understand, right? So when I tell you, hey, find sine of 74 degrees, what are you finding? Well, you could say, okay, if I'm in a triangle, sine of 74 degrees is the ratio of the opposite divided by the hypotenuse. Okay, great. If I'm in a circle of any radius, what I'm finding is the ratio of the y to the radius. Okay, so the further I go out on that terminal side, the bigger my y is, but the bigger my r is, but the ratio stays intact. Or the third way that we can look at what the heck sine of 74 degrees is it's quite simply the y-coordinate. It's the y-coordinate from the unit circle with a radius of 1. And this really is a nice, simplistic way of trying to understand, hey, we have an input, an angle goes into a trig function. What you get out needs to represent something. And if it's a triangle, it represents ratios of sides. If the radius is not 1, it represents the ratio between the lengths of that triangle and the radius, right? The x, the y, and the r. But if you're in a unit circle where your radius is just beautifully 1, then it really just represents the y-coordinate from the unit circle. So I still want to emphasize the same thing I've emphasized before. Anytime we're working with 45 degrees, 30 degrees, or 60 degrees, I still do expect exact answers, okay? And that would be the same for pi over 6, pi over 4, and pi over 3, because those are just the radian equivalents. So moving forward, when we see angles inside of sine, cosine, tangent, cosecant, cotangent, whatever, I still expect answers, right? But if it's one of these beautiful angles, then I definitely expect them to be perfect, right? I expect them to be exact. And the interesting thing is that even if it's positive or negative, doesn't matter. Negative 30 degrees is the same angle just going down. And even a multiple like 120 degrees. 120 degrees is clearly related because if you draw 120 degrees, it's 60 degrees from the x-axis, right? So that's still a 60-degree angle. Even though it's 120, it's still a 60-degree angle. So one final thing I kind of want to show you here and really go over is this next one is, don't get overwhelmed by this, but this is really awesome. I'm actually going to provide you a PDF of this. This is a unit circle, and everything is labeled on this unit circle. This is really awesome. So first off, please remember this is a unit circle, so the radius is always 1. And you can see that right here by understanding that this first point right here is 1, 0. And the first thing on this is I have all the perfect angles that we love: 30 degrees, 60 degrees, 90, 120, 150, all multiples of 30, all the way to 330. Even 360 is a multiple of 30. And then even 45, right? Multiples of 45. 45 times 2 is 90. 45 times 3 is 135. 45 times 4 is 180. And then again, keep going, 225, 270, 315. And I also have the ratings on here. And I want to talk about the ratings real quick, because one thing I love doing, I know this is sad, but I find enjoyment in this, is counting my ratings. So I love counting by 6. Everybody should love counting by 6, especially with the unit circle. So here we have 1/6 pi. This would be 2/6 pi. And that makes sense. 2/6 reduces to 1/3. Here we have 3/6. 3/6 reduces to 1/2, 3/6. 4/6. 4/6 reduced to 2/3. 5/6. 6/6. 6/6 is 1 pi. 7/6. 8/6. 9/6. 10/6. Excuse me. 11/6. And then finally 12/6. 12/6 would be 2 pi, or a full circle. And what I'm trying to get at here is that if you notice now, look at pi over 6, right? Pi over 6 is 30 degrees. Notice the coordinates for x and for y. That's based on knowing a beautiful 30 degrees. Like, if you really need me to draw this one more time, I will, right? This is my 30-degree angle, and we know that the shorter leg is a, the longer hypotenuse is 2a, and the long leg is a radical 3. But if the hypotenuse or the radius is guaranteed to be 1, well, that means that a is 1/2. And that means that the bottom leg is radical 3 over 2. So notice at 30 degrees, sine is the y-coordinate, 1/2. Cosine, the adjacent, radical 3 over 2. That's the x-coordinate, right? This is beautiful. But notice, like, if I come over here to 150 degrees, 150 degrees directly corresponds to 30 degrees. Because 150 degrees is 30 degrees from the x-axis. That's that reference angle we talked about before. So notice that the coordinates for 150 degrees are the exact same as 30 degrees. The only difference is the x-coordinate is negative because I'm in quadrant 2. And then I can even come straight down to 210 degrees. 210 degrees, once again, has that same reference angle of 30 degrees from the x-axis. So 210 degrees is really no different than 30 degrees. And look at the point. It's the exact same point. The x is radical 3 over 2. The y is 1/2. The only difference is they're both negative because we're in quadrant 3. And then I could go let's see here. Let's also go straight across to 330 degrees. 330 degrees also has a 30-degree reference angle. So notice its coordinates are exactly the same. Radical 3 over 2 for x, negative 1/2 for y. And again, the only difference is the y is negative because we're down in quadrant 4. So what I'm trying to get across to you guys is that any multiple of 30 is going to act like 30. So 30 degrees, 150, 210, 330, they all have that same 30-degree reference angle. They're all going to behave the same. And again, it's all based on this. It all goes back to that special triangle. But again, you have to understand that I'm forcing the hypotenuse, the radius, to be 1, which makes a 1/2. That's the height, y. And the adjacent side is radical 3 over 2. That's the x-coordinate when you're on the unit circle. And this is all awesome. I really hope so. So again, I should be able to ask you questions. I should be able to say, hey, what's cosine of 5 pi over 6? Well, all you have to do is find it. And remember, cosine is the x-coordinate. Negative radical 3 over 2. There's your answer. Don't believe me. Check on your calculator. Put yourself in radian mode. Type in cosine of 5 pi over 6, and you will get negative radical 3 over 2. But again, all I had to do was open my eyes. I had to look for 5 pi over 6. And once I found 5 pi over 6, I remembered, hey, go back here, right? Remember, cosine is the x-coordinate as long as you're on the unit circle. So this is the unit circle. It has a radius of 1. So bingo, there it is. Also, let's do a couple more. Let's do tangent of 5 pi over 4. So once again, find 5 pi over 4. Tangent is the y divided by the x. That's going to be negative radical 2 over 2 divided by negative radical 2 over 2. So first off, two negatives make a positive. And what's radical 2 over 2 divided by radical 2 over 2? Well, that's the same number divided by itself. Boom, that's 1. Easy, so easy. All right, let's do a couple more here. Let's do some tricky ones because, let's talk about pi real quick. So let's do cosine of pi. Now, if you draw pi, that's an angle that goes directly over here, 180, you actually don't have a triangle. It's just a line, right? There's no triangle, but that's okay because we still know that it's the x-coordinate. So cosine of pi is negative 1. It's the x-coordinate. All you have to do is find the angle, give me the x-coordinate because that's what cosine is. What is sine of pi? 0. The y-coordinate. Look at it. It's right there. It's the y-coordinate. So simple. Now, be careful, though, on problems like this because, for example, if I ask you, hey, what's cotangent of pi? Well, by definition, please remember, cotangent is x divided by y. So if I do x negative 1 divided by y 0, I actually get does not exist. This is UND, undefined. So cotangent of pi is undefined because you can't have a 0 denominator. Same thing can be true for pi over 2. If I were to ask you for tangent of pi over 2, that would be the y-coordinate 1 divided by the x-coordinate 0. And again, can't happen. That's undefined. So that's going to happen. It's no big deal. It's totally fine. In my mind, it's actually easy to think about. So again, when you are on the unit circle, life is actually easy. Life is actually great. If I ask you about an angle, all you have to do is find it. And all you have to remember is what's on here. Sine of an angle is the y-coordinate. Now again, it's still y over r. I'm not changing that. But if the radius is 1, well, y divided by 1 is just 1. By the way, check out this marker. Look, when you write, it's like stars. Anyway, pretty cool. All right, so the point is this unit circle is awesome. And again, don't even add this. Right? I'm going to actually give this to you in a PDF that you could add. But if you want to add this to your cheat sheet on your own, that's fine. Just a lot to write. But what I want you to look around here is that all of these values are exact. And they're exact because they're all related to either 30 degrees, 45 degrees, or 60 degrees. So if I ask you about one of those values, or if I ask you in radians, pi over 6, pi over 4, pi over 3, or any multiple of 3 pi over 4, 5 pi over 3, you should instantly be able to give the exact answers. And again, you have this chart. I'm going to give you this unit circle. So you don't even have to really do any work other than look. Let's just do one more. Cotangent of 11 pi over 6. Okay, first thing is find the angle. Okay, here's 11 pi over 6. I found it. Then you have to remember, cotangent is x divided by y. Okay, so I got to take x, radical 3 over 2, divided by y, negative 1/2. Now, what I would recommend doing is instead of dividing, I would multiply by the reciprocal, -2/1. That cancels out the -1/2 because you multiply by the reciprocal. The 2's cancel out, and we'd get -radical3. So there you go. Cotangent of 11π/6, with a little bit of dirty work, got my hands dirty a little bit there, is -radical3. Now, of course, the question comes from some students, well, what if I ask you about an angle that's not on here? Okay, well, let's do it. What if I ask you for, I don't know, sine, that's not a good marker, sine of, let's see here, 216 degrees. Well, obviously 216 degrees is going to be somewhere right around here, a little bit more than 210 degrees. But again, it's not a perfect angle. I'm not going to know it. It's not a multiple of 30, 40, or 60. So I'm going to have to go to my calculator. I mean, no sweat. Go to your calculator, sine of 216 degrees. I'm going to tell you right now, it better be negative because I'm in the third quadrant. Sine relates to y. So it's -0.588. -0.588. Okay. That actually should make sense. I mean, at 210 degrees, the y-coordinate, or the sine value, is -1/2. And I'm a little bit less than that, so it should be a little bit less than -1/2, so -0.588. It actually kind of makes sense. I hope it does. But again, that's the y-coordinate. Yeah, don't forget you got to divide by the radius. Well, the radius is 1. This should be easy. So this is the unit circle. It's really meant to be very simple and more of a kind of a simplistic way of understanding all these values. Just know that we really care most, or we care to be exact at least, for those multiples: 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330. There they all are. And then we also love the 45, 90, 135, 180, 225, 270, 315, the 360. We love these angles. These are the angles we love, right? These are the beautiful angles we love. And why do we love them? Because we could draw those two special triangles to really understand the coordinates. Let's talk about 45 degrees here, just to kind of end this off, right? There's 45 degrees. We all love 45 degrees. We know, if I kind of draw that 45 degrees, we know that the two legs are both A, and that the hypotenuse is A radical 2. But in a unit circle, I'm forcing the hypotenuse or the radius to be 1. If I'm forcing that to be 1, let's figure out what A is. So 1 is A radical 2. And if I divide by radical 2, that means that A is 1 over radical 2. But of course, we don't like square roots in denominators, so we're going to multiply top and bottom by radical 2, and we get radical 2 over 2. So both of these values, both A's, are radical 2 over 2's. Okay, that's just, again, I'm not making this up. I'm understanding this through my special triangles. So this point right here has an x value, the adjacent side of radical 2 over 2, a y-coordinate, or an opposite side of radical 2 over 2 as well. And again, we saw that on the unit circle. There it is right there. Looks like a holiday thing here with all the green and red. So again, what I'm trying to get at is that I'm not changing anything, right? We still have this connection between triangles and now points on a unit circle, and it's all the same. We're just trying to connect everything together so all the pieces of the puzzle fit together and that you truly understand trigonometry. Because I want you to say, I understand what sine of 45 degrees is. To me, it's not just something I get on my calculator. It's not just something I memorize. I understand what sine of 45 degrees is. I understand it through a unit circle. It's the y-coordinate. In a non-unit circle, in a bigger or smaller circle, I understand it's the y divided by the radius. Or if it's a triangle, I understand it's the opposite divided by the hypotenuse. I know what sine of 45 degrees represents. And I really, truly hope by the end of this that you guys do understand that, and that now we can really start kind of working on some solid problems and spending some time really working through problems to prove that we understand everything there is to know about trigonometry. All right, guys, that's it. Hope everything made sense. Be ready to ask questions if you need to.